Good evening to all. I am Rakhi Yadav, your PMRF teaching assistant for pericyclic reactions and organic photochemistry course, which is conducted by NPTEL and whose course instructor is Professor S. Sankararaman from IIT Madras. So, students, in week 6, we are going to cover in reaction and some introduction to organic photochemistry. So, in pericyclic reaction, our last topic is in reaction. Till now, what we have studied in first week, we have covered electrocyclic. Then followed by we have studied some cycloaddition, 2 plus 2 or your Diels-Alder reaction. Then we have studied about sigma-tropic rearrangements, right? And after that, we are going to cover in reaction. Just give me 1 minute. Okay. So, what are in reaction? The joining of double or triple bond to an alkene. So, what they are saying that joining of double bond or your triple bond to an alkene having a transferable allylic hydrogen, right? Let's say here we have methyl group. So, these hydrogens are at allylic position with respect to this double bond. Yes or no? So, the joining of this double bond to an alkene having allylic hydrogen, right? That is called your in reaction. In reaction can be of three types. One is your intermolecular, second is your intramolecular, and third is your retro. Are students joining or not? Okay, before starting main thing, let's just wait for 1 minute more. Um, Hello, Prashant. Am I audible? Hello. Prashant, are my slides visible and am I audible? Yes or no? You can write in chat if you are not able to open your mic. Just tell me if I'm audible and my slides are visible. Okay. So let's start today's class. So in last 5 minutes, I have discussed about in reaction. Basically, in reactions are joining of a double or triple bond to an alkene, joining of double or triple bond to an alkene having allylic hydrogens, right? So basically, this reaction can be seen like your Diels-Alder reaction. One will be your ene, another will be your enophile. The moiety which are having allylic hydrogen are known as ene, and the moiety onto which your hydrogen are going to attach after that in reaction, that moiety is known as enophile. As name suggests, your enophile should be electron deficient, right? So, ene reaction can be of three types: intermolecular, intramolecular, retro. So, one by one, we are going to cover these reactions. So, just have a look at this. Look at it. This is your ene, right? Why? Because this is having allylic hydrogen. Yes or no? And this is your enophile. So, basically, hydrogen moves from here and gets attached to your Y. What enophile you can encounter? These are the possible enophiles: your alkenes, alkynes, carbon monoxides. Oh, sorry, here they are ketone, thioketone, your imine, oxygen, and your N2. So these are the possible enophiles which you can encounter while solving these questions. So let's see first intermolecular ene reaction. So till now you know the basic mechanism how these reaction work. So you should know if there are two components, then reaction is termed as intermolecular ene reaction. Basically hydrogen will transfer from here, right? And now one thing arises, that why hydrogen is basically, if by regioselective purpose, if we are looking at this reaction, you can think of it, it's like in the way that this hydrogen is removing here as H plus. So basically this is going to attack here, yes or no? So among these two positions, where will your H plus go? Where your negative charge will be stable, yes or no? That's why hydrogen gets transferred to this alpha carbon to carbonyl chloride, and this allylic system bonded to this beta carbon, and this is your ene reaction. Similarly, this is another example for your intermolecular ene reaction. Hydrogen is going to transfer from here, okay? If it goes like H plus, right, so here negative charge will come. This I am telling only for understanding purpose. All these reactions are taking place in concerted way. But for understanding, you can think it of as negative charge is going there, then this negative is going to attack here, and this negative is going to take this H plus. Yes or no? So this is your intermolecular ene reaction. Now what is your intra? In intra, that enophile is embedded within the system. Yes or no? So allylic hydrogen is going to uh, take allylic hydrogen is going to transfer from here, and on the basis of enophile tethered to your ene. I'm repeating again. On the basis of enophile tethered to your ene, these reaction can be classified as type 1, type 2, type 3 on basis of number of carbons in between your ene and enophile. Okay. So let's solve problem number 1 for today's session. Let's take 1 minute pause and try to solve this question. And just tell me product of this reaction. Basically, pent 1,4-diene is made to react with your maleic anhydride with 2 moles of maleic anhydride, and heating condition is given. So how will you attempt this question? Since we are studying today in reaction, so obviously in reaction is going to take place. So can you start this question? Prashant, have you understood what is in reaction basically? I have given short intro. And understood, or I can explain again if you will say. I couldn't hear you. Wait. Okay. I'm audible? Okay. Uh-huh. Could you please repeat your question? What you want to send with attachment? What assignment? Okay, okay, you can send there. Actually, these assignments and all, na, I don't check. These are checked by internal authorities. We don't use to check. But you can send. Are, Same thing I am repeating, na. All these things we don't handle. Huh. But are you able to solve assignment questions? If not, you can ask your doubts in these tutorial session. These are meant for that only. Because we can't solve the same questions which are given in assignment, right? So we take some example from them and try to showcase here. Okay. So you got the introduction of in reaction. What basically are in reactions? Exactly. है ना? And as the name suggests, your ene should be electron rich and enophile should be electron deficient, right? Now see, how are you going to approach this question? Wait. See, if this system is conjugated like this, then to which reaction is possible among this and this? Tell me fast. Exactly. But in the present case, these alkenes are not conjugated, right? So, one more possibility is that we can see the possibility of 3 3 sigma tropic, but that can also be not done. Why? 1 2 3, but 1 2 3, no, right? No sp3 carbon is there adjacent to 1. Are you getting what I am trying to convey? Wait. 1 1 2 3 and 1 2 3. If this system is there, there is possibility of your sigma, right? If this system is there, there is possibility of your Diels-Elder. But here in this case, nothing is there like this. So what another possibility is there? Let me tell you. There are two hydrogens here. Yes or no? And these are allylic. Okay. So what can we think of that one is going to attack your one molecule of malic anhydride. So what you will get? Let me draw. One hydrogen is going, so double bond will come here, and this carbon is going to attack to your enophile. Till now it is clear, Prashant. Simply simply this hydrogen has transferred to your enophile. Okay, now if you can see, this has become your diene. Yes or no? And we have another molecule of malic anhydride in our system. So now in reaction followed by your Diels-Elder. In reaction followed by Diels-Elder. Yes or no? Yes. So take this as your diene and react it with your, this is your dienophile, and you will get this product. Let me erase that part. So basically allylic hydrogens are present, So first in reaction will take place. Now, since it has become your diene, this can take part in 4 plus 2 reaction and you will get this product. Understood? Another student is also joined, I think. Okay. Let's move ahead. So, can you try this problem number 2? Basically, this protected, what we can call it, ketal. Protected ketal is given to you, right? And made to react with this alkyne in presence of Kf. Forget about the answer. Just tell me, just looking at reaction condition, what is your first step? Okay, let me tell you functions of every reagent, right? Kf is your fluoride source, which is going to deprotonate, not deprotonate, desilylate this compound, starting material. 18 crown 6 is your phase transfer catalyst because these are your organic compounds and Kf is your inorganic reagent. So in order to ensure the solubility, they have used 18 crown 6. They are also referred to as phase transfer catalyst. THF is your solvent, tetrahydrofuran. RT temperature. Now tell me, what is your first step in this reaction? Another hint. In reaction will take place. Now tell me what can be the product. Just try. Tell me wrong product doesn't matter. But try yourself. I'm also solving. So students, at first Kf is there. Kf is going to give F minus, right? And F minus is going to attack to your silicon and it will leave as your silicon Me trimethyl fluorosilane, right? And it will leave negative charge onto your benzene ring. And we have a good leaving group. So, what intermediate will form? Benzyne. Yes or no? So, your enophile is ready. Now, you have this ene. Basically, you have to transfer one of the deuterium to this benzyne and your job is done. First of all, this will transfer here and this will go there. Okay. I'm not drawing that ketal part as this will be untouched in this reaction and deuterium will be transferred to this carbon. Have you got this product, Prashant? Or you have and are you thinking of the fact that this deuterium can be transferred to this side? That is also a possibility, but it will not break this aromaticity. Okay, so it will transfer this deuterium from this side only, and this is your final mechanism. So basically, in this reaction, first your fluoride is going to attack in vacant d orbitals of silicon. It is going to desilylate this compound. Negative charge will come here. It will go there, knock off your triplet ion, and will form your intermediate benzyne. That is attacked by this moiety. Basically, moiety having allylic hydrogen or deuterium. In this case, deuterium is there, and At last, this allene will form. These type of species are known as allene. Okay, when there is continuously two double bonds are situated. So problem number 3 for today's session is this. Try. Okay, taking help from previous problem, just tell me what is your first step. Just now we have solved. Prashant, what will be your first step in this problem? Formation of benzene. Yes or no? Huh. Then what is the possibility you can see in this question? See, today we are going to solve question based on in, but along with that other reaction can also be used, right? Your Diels-Alder, electrocyclic. So you should keep all the reaction in your mind before solving these questions. Now one side you have benzene, another side you have what system you have? Can't you say this diene? So let me give you hint. You just try to solve. You have benzene, you have diene. First, Diels-Alder reaction will take place. Why? Because this is not a system which is having allylic hydrogen. Yes or no? So try to solve. Another thing is that, let me use pen. You can take two molecules of this. Now solve. Okay. Let me start solving for you. First, benzene will form, and you are given this system. In exam they can give you like this, PHC double bond C, right? There you can't imagine where is diene, but when you will write its open structure, you can easily see one diene is there. So first Diels-Alder reaction will take place. How? You got this product till here? Yes or no? Now you are having these allylic hydrogens, correct? And since two molecules of this system has taken two molecules of this triplet, so you have in your system one benzene. So now in reaction will take place. Yes or no? You have to transfer one of the hydrogen to this system. Yes. Let me draw final product for you. You also draw and match your answer. You get this product. So you can check your answer from here. So first, in presence of fluoride ion, your benzene will form, yes or no? Then 4 plus 2 reaction will take place. And now since it is having your allylic, but one mistake we have done is that there are two transferable allylic hydrogens. From here also it can take place, and from here also it can take place in your reaction. But what is the possible reason of allylic hydrogen going from here? That aromaticity of this ring is coming back, yes or no? Therefore, uh, instead of these two allylic hydrogens, this ring junction hydrogen is going to take place in your in reaction. Understood? Yes or no? Okay. So this is your problem number 4. This aromatic compound is going to react with selenium dioxide in acidic condition. Okay, if you don't know the mechanism, could you please tell me, in presence of selenium dioxide, what will be the product? Just on memory basis, what is the role of selenium dioxide? It is having two roles. One role is with ketone, and one role is with your allylic system. Whenever ketone is there in medium na, selenium dioxide changes that ketone to diketone. And whenever you are having allylic system, so basically it made your allylic alcohol. Have you read this function of selenium dioxide? Prashant, if you are not speaking anything, kindly mute yourself. Okay, okay. So basically here we are going to study the mechanism of ketone to diketone. Could you please give me hint how to start this question? So, see, you are having selenium dioxide. This is your ene system. Take it as your ene. This is your enophile. Just transfer one of the hydrogen, okay? And see what you are getting. If you transfer one of the hydrogen, double bond will come here. It will be your O, selenium, double bond O and OH. Where this OH came, this hydrogen went to one of the oxygen of selenium. Okay. Till this point, it is clear or not? Okay, good. Now you can see this is your 1, 2, 3 system, and this is your 1, 2. And which type of rearrangement now can take place? 2, your 2, 3 sigma tropic rearrangement is going to take place. Okay. Huh. Just draw that product, you will get your answer. So basically from here oxygen is going to connect selenium, OH, this double bond oxygen will come back. Yes or no? Now hydrogen from here will go and it will eliminate selenium and H2O, and you will get your diketone. If you have any problem in mechanism, just tell me, I will explain you again. So this is your mechanism. See, first you just have to apply this mechanism here. You will get diketone here. Okay. So first, hydrogen is going to transfer to this your selenium dioxide. Then this selenium double bond O can be written as selenium plus O negative, or you can write it in is in double bond form also. Both are correct. So 1 to 1 to 3. Then 2 3 sigma tropic shift will take place. Hydrogen will go from here with removal of selenium in H2O, and this ketone will change to diketone. Understood? So basically your final product will be, so from today you should remember whenever you have ketone and you are given selenium, okay, just draw carbonyl to its adjacent methylene carbon. Okay. So this is your product. Yes or no, Prashant? Okay, good. Next, next is an example of intramolecular in reaction. Just try to solve it by giving it proper numbering, then you will get answer. And I am expecting this answer from you first. Take your time and tell me the answer. We have solved enough questions on in reaction. If you are not able to solve, no problem. Just tell me, okay? Wherever you got stuck. See, these are your allylic hydrogens. Yes or no? You just have to see. Here also you are having allylic hydrogen. In intermolecular in reaction, your hydrogen is transferred to this system. How? Double bond will come here and this hydrogen went to this alkene. Yes or no? This is example of your intermolecular in reaction. But here in here this system is tethered. Tethered means all the functionalities are present within the same molecule. So hydrogen will go from there and it is going to attack here. Basically this reaction takes place in exo mode. Okay. So how many membered ring will form? One, 2, 3, 4, 5. Okay. So 5, just draw 5 membered ring. 1, 2, 3, 4, 5. At 5 number carbon, one carbon is there with, that will have this hydrogen, one of the allylic hydrogen, right? And you will get this system. Why? Because this bond shifted to here and this shifted to there, and you will get this product. So this type of product is in two option, option number A and option number B. But you should remember the fact that in reaction, one of the ring is forming of 5 membered, and another is if you draw the transition state by keeping this same. Right. So how many membered ring is forming? One, 2, 3, 4, 5, 6. So basically, one of the ring is forming is 5 with transition state having 6 membered ring of that in transferring hydrogen, right? So whenever you got 6 5 fused cyclic system, 6 5 fused cyclic system, always Cis junction is favorable. Cis junction is favorable. Okay. So correct answer is A. You can draw it also. Whenever you are having fused system, na 6 5 6 6, generally cis junction is more favorable. Not in 6 6, but I will say in 5 5 or 6 5. Yes or no? Good. Here the correct transition state has been shown. Just you can have a look over it. So basically, if you write this bond in this way, this they have drawn envelope form. Why? Because one of the ring is forming is 5 membered. So allylic hydrogen are transferring from here, and you will get this folded bicyclic transition state, and you will get this product. Okay. Now tell me the major product formed in the reaction sequence is. Let me write this reagent in open form for you. What type of functionality is this compound? Tell me. This is your base. Now tell me, what type of functionality is this? Active methylene, yes or no? A carbon is sandwiched between two electron withdrawing groups. Okay. Aldehyde is there, base is there. So obviously first base is going to deprotonate this hydrogen. Okay. And then they are going to basically, which name reaction is this? Active methyl aldol reaction between aldehyde and your active methylene compounds. Which type of condensation is this? But aldol reaction takes place between two aldehyde or two ketones, or a mixture of aldehyde and ketone. But here one is your aldehyde, another is your active methylene. Another name reaction starting from K. Cannizzaro reaction takes place between two molecules of aldehyde in presence of strong base such as concentrated sodium hydroxide. Another option, tell me. Noe-Vinegal condensation reaction. Okay, basically whenever you have RCHO and active methylene compound, you just have to replace this carbonyl oxygen with your this group. This is your simple Noe-Vinegal condensation product. Okay. What new reactions you have studied today? One is your selenium dioxide function. It will change your ketone to diketone. Whenever you are given ketone and on arrow it is written selenium dioxide, close your eyes and draw diketone over there in product. Okay. Another is your Noe-Vinegal condensation. Basically, this C is going to clear. Now tell me in second step which reaction will take place. Now that we have done so many questions, you can easily tell me, huh? What? I couldn't get you what you are telling. Annihilation? Okay, okay, wait. This sodium methoxide you are telling me. This is sodium methoxide. Na? Methoxide is your base. Huh. Sodium methoxide, how can you form sodium methoxide? When you treat your methanol with sodium, it will form sodium methoxide. Okay. Sodium methoxide or alkoxides are known to be a strong base in organic chemistry that can abstract these active methylene protons. First, enolate will form that is going to attack your aldehyde carbonyl. Okay, let's move ahead. So basically now in reaction will take place because allylic hydrogen are there. How many ring? Actually, I couldn't get which reaction you are talking of. Acha, in. Huh. Yeah, you are correct. Na in reaction will take place. So six-membered ring will form. Let's say this is your carbon number 6, 5. On carbon number 4, your methyl is there. Correct? 3, 2. And at carbon number 1. And at carbon number 6, these two CO2 Me groups are there. Correct? Are you sure? Understood now? So this is mechanism. Let me erase my part. Now see, first sodium methoxide is your base that is going to abstract active methylene protons. Okay. Then this negative charge generated is going to attack carbonyl of your aldehyde. Okay. And then reaction will take place and it will form this type of compound. Now in reaction is going to take place and you will get this. Most important thing is you can draw these in reaction in your chair form, right? In order to get this stereo. Because they underwent in reaction via chair like transition state. So you can see here, let me explain you. This hydrogen is going to transfer to this carbon, yes or no? Because this hydrogen is going to transfer to this carbon. They have drawn six-membered chair of that in reaction, and you can see that at this carbon CH containing 2 CO2 Me, this is going above. So in product this is above. Okay, this group is below this allylic group, so that's why this group is below, and this methyl is above, so it is above only. So that's how they have drawn stereo. So this is a very good example of stereochemistry of in reaction. You just have to draw chair like transition state, you will get the stereo. Okay. So problem number 7, you just solve and tell me the answer. I am also solving, just you try. Let me give you hint. Again here allylic hydrogens are there. You have enophile in your same system. One, two, three, four, five. Five-membered ring will form. Yes or no? Just number them. You got this product? No. You got, okay. So at 5 number carbon, what will be the CH2 CO2 Yes or no? So this is your final product. Now tell me, junction would be cis or trans? Yes, junction will be cis. So this is your product. I have drawn down, sir. Okay, good. This is, I think, last problem for your in reaction. No, no, more problems are there. Okay, solve this question. One is your one, two, three, one, two, three. Isn't, yeah, exactly. Wait. Cope rearrangement or Clausen rearrangement? Exactly. Now you know that it is your Clausen rearrangement. Now just form the product and tell me among these two products which is the product for Clausen rearrangement. This is your product A or B. Which is the outcome of your Clausen rearrangement? I am also drawing. You also try. Product A is your outcome of Clausen. Are you sure? Okay, I am also drawing. You draw. Now, tautomers will take place. So, you were right. A is your outcome of Clausen rearrangement. Yes. And B? Let me erase this part and explain. See, first you were very right that it underwent 3 sigma tropic shift. Since oxygen is there, it will be a Clausen rearrangement. Okay. After 3 sigma tropic, tautomerism will take place and it will form your phenol. Correct? And this is your product number A. Why this arrow is bigger in this side? Could you tell me? This arrow, reversible arrow, is greater than this side. Why? It shows no. On which behalf we make this arrow? Okay, let me explain you another thing. This is your one arrow, reversible arrow. Okay, this is your another arrow. B, A, B, A, B, and this is your another arrow. Now tell me the difference between three reversible arrow. See, these arrows suggest that A and B forms are interconvertible. When this equilibrium arrow is of same size, na, it means stability of A and B both are comparable or same, similar. Okay. When this arrow is more towards your A side, it means stable A is more stable than B. When this arrow is more towards B, it means B is stable than A. Okay. Because here, apart among these two systems, this system is more stable due to aromaticity. Therefore this arrow is more towards this. Okay. Okay, good. Now Since you are having this product of your Claisen rearrangement, and you know that allylic hydrogen are there, and this is your in reaction. So first in reaction will take place. Okay, hydrogen will go from there and it will transfer to this alkene. Now this three-membered strain ring system has been formed. Let me highlight it. Hmm. Now this three-membered ring has been formed, right? And you know that three-membered rings are unstable. Okay, so retro in reaction will take place. Hydrogen will go from here and will break one of this bond to. In this way, two things are done. One is they get aromaticity back, and another is the another is release of ring strain. Okay, and you will get this product. Yes or no? Okay. Now solve this problem. Huh. So this is your last problem for in reaction. Then we will have short intro for organic photochemistry and the class will be over. Okay, take your time and try to solve this. In first reaction, what is your opinion? Okay, let's go one by one. We have started studying pericyclic from electrocyclic. Okay, is there any possibility for electrocyclic reaction here? Where from where you can do? Okay, so uh, how you are going to solve? See, electrocyclic reaction will form when you have your cyclobutene. Okay, then it can open. Yes or no? 4 pi electrocyclic ring opening. But here cyclobutane is there, not cyclobutene. Now heating is there. Diels-Alder reaction requires two partner, but here only one partner is there. Then we have studied sigma tropic. In sigma tropic, 3 3 system type is visible when we do numbering, but here that also is not possible. So only okay, okay. I will use red pen. Okay, wait. Now, now it is visible now, Prashant. Okay. Hmm. See, I have talked to you that electrocyclic can't happen. Deal solder requires two partner. That also can't happen. Sigma tropic requires this type of system. Okay. So this is also not possible. Now last possibility is your retroene. In reaction can also take place, but there are no allylic hydrogens. Okay. So here retroene reaction will take place. Hydrogen will go from here and you will get this enol. Enol will obviously tautomerize to your ketone. Okay. Now, just what they have done is again return this in enol form, But this time they have abstracted this hydrogen from this side. Okay, apart from internal olefin, they have made exo-olefin. Yes or no? Now this is your allylic system. This is your ene. Ene reaction will take place and you will get this system. Now let me tell you how to do numbering. Okay. See, this hydrogen is going to migrate here and this is going to attack here. Okay. So how many member ring will form? One, two, three, four, five, six membered ring. So basically they have just joined that carbon. Which carbon? That this carbon directly to this carbon. Okay. And in between how many? One, two, three. Three carbons are there. Yes, three carbons are there. So in total six membered ring formation has taken. Have you understood this question? Basically, main funda of this question is retroene. When you will solve many problems of such type, na, you will get that what can be my first step. Okay. So I hope till here in reactions are clear. There are three possible reactions: intermolecular, intra, and retro. I have covered questions related to all these three types of in reaction. Just go through all these problems and I will suggest you to solve these problems without seeing solution and start and try to solve by yourself and then match your answer. Okay. Okay, let's start organic photochemistry. Wait. So, organic photochemistry. As the name suggests, use of photochemistry in organic. Use of photochemistry in organic is your organic photochemistry. Basically, if we look at pericyclic reactions, they are also photochemical reactions. Yes or no? Some are thermal but photochemical. When we are not adding any reagent externally and we are making use of heat and light, that is known as your organic photochemistry. What they have written is molecular organic photochemistry is that part of science which relates structure dynamic process that result from interaction of light with organic molecules. So basically, whenever you incident any light to your organic molecule, the reaction it is taking place, that is your organic photochemistry. Organic, that organic compounds. Photo means light. Chemistry, their chemistry. Whenever light is falling on your organic compounds, that is known as your organic photochemistry. Now in organic, these are your energy levels, right? Sigma. See, this energy order is via stability wise. So bonding orbitals are lowest place, as these are most stable. Sigma, pi, non-bonding, pi star, sigma star. Okay. The orbital which is most stable, its anti-bonding is going to be most above or most unstable. Okay. Pi star and n will be there. N is nothing but your lone pair, such as in oxygen, in a water molecule, oxygen is having how many lone pairs? Prashant, in H2O oxygen is having how many lone pairs? Two, na? So those are your non bonding lone pairs. Okay. So they told that the order of energy, how much energy you have to give for any transition to take place, depends on these energy orders. So sigma to sigma star will have highest energy because energy level is, you can assume it as your hotel rooms, hotel room 1, 2, 3, 4, 5. To go from room number 1 to floor number 1 to floor number 5, energy required will be greatest. Yes or no? From n to sigma star, it will be quite less. From pi to pi star, it will be less. And from n to pi star, that is only one room away, that will be least. Okay. So sigma to sigma star transition can be seen in your alkenes, because alkanes have nothing but CH or CC sigma bonds. Yes or no? They don't have lone pairs, they don't have pi bonds. Alcohols, amines, ether, they have heteroatom having lone pair. So N and sigma star. Why other orbitals can't take place in alcohols, amines, ethers? Because in these type of system, no pi bond is there. Okay, pi bond. If pi bond is there, then only pi star can come. Yes or no? Okay. In aldehyde carboxylic esters alkenes, pi to pi star. Why? Because pi bond is there in aldehyde in and alkenes. Okay. So this is conclusion of this page. This is a Jablonski diagram. Let me explain you. So basically, first your organic molecule is at ground state. Okay. At ground state, let's say you are incidenting a light. It will absorb that light, and on absorption it can go to two singlet excited state, S1 or S2. Okay. Let's say one went to S2 and one went to S1. Now, if after going from S2, it is coming back to S1. This is singlet state, this is singlet state. Same multiplicity if your molecule is coming to ground state from excited state without changing its multiplicity, that is known as your internal conversion. Okay, as it is shown by red. Now see, this is coming from singlet to triplet. Multiplicity is changing, therefore inter-system crossing. These are terms used in physical chemistry for absorption phenomena. If you have studied about UV absorption, you know what are the singlet and triplet excited state? Okay, okay. See, let's start from basic. First is your absorption. Whatever light is incidenting on your compound, how much light it has absorbed, that is known as your absorption. Okay. Now fluorescence, phosphorescence, these terms are given on basis of multiplicity. Let me change color. Huh. See, in fluorescence, your compound is coming from singlet to singlet state. It means no change in multiplicity. In phosphorescence, it is changing from triplet to singlet. In internal conversion, singlet to singlet. Intersystem crossing, singlet to triplet. Forget about this vibrational relaxation. Basically, vibrational relaxation is whenever your molecule excited to higher state, na, after you leave it for some time, it will be relaxed to its ground state. Okay. Whenever you go upstairs, always a person wants to come downstairs, right? Because ground state has maximum stability. In same way, these molecules excite first, then they wanted to come to ground state in order to attain stability. That is your vibrational relaxation. And these terms are given on basis of these multiplicities. Singlet, triplet, if you want to know, if two spins are like this is in plus half, this is minus half. Total spin 0, and s is given by 2s plus 1, so it will be 1. So this is your singlet. If electrons are kept like this, S is equals to half, half. Total spin 1. 1 half plus half 1. So 2 into 1 plus 1, 3. This is your triplet state. Okay, understood? In general, in ground state, your all the electrons are paired, yes or no? So they will be in singlet state in ground state. But during excitation, whenever you excite photons, the singlet state sometimes changes to triplet. One of the spin got invert from minus half to plus half, and then changes to triplet state. Understood? Okay, good. So I hope you got this Jablonski diagram. Just go through Sir's lecture also. He has also explained Jablonski diagram. You can get question based on that. If a molecule is coming back to its ground state from S1 to T1, which type S1 to T1 by one more thing that I have missed here is next time when I come, you should come with this answer. In all these five phenomena, na, wait, my pen is not working. Hmm. In all, see, molecule can come from higher excited state to lower excited state in two ways: radiative, radiative, and your non-radiative. Radiative means by release of heat. Non-radiative means without releasing heat. So in next class I am going to ask you fluorescence phosphor in among these five process, which are radiative and which are non-radiative. Okay, radiative and non-radiative. You just read all these things. I will ask you in next class. Okay. Multiplicity, I have told you that in fluorescence multiplicity doesn't change, but in which two cases multiplicity change? In phosphorescence and intersystem crossing. Okay. And in internal conversion and fluorescence multiplicity doesn't change. Okay. Then there are two laws of photochemistry. One is your Grother's Draper law. In that, according to this law, this is very simple law. They are saying that only the light that has been absorbed by a organic molecule. Let's say you have given a molecule 100 watt intensity light, right? But it has absorbed only 60 watt intensity light. So they are saying that 60-watt light is responsible for a photochemical change. Let me read for you. It is an empirical law which states that when a substance is irradiated, only that fraction of radiation that is absorbed by the substance can bring photochemical change. Okay, understood? They are saying only that fraction of radiation, means whatever light that a molecule has absorbed can bring photochemical changes. Okay, the light which is reflected or scattered or transmitted play no role in chemical changes. It is obvious that whatever light that molecule will absorb, that only it is responsible for its chemical change. Okay. Second law is your Stark-Einstein's law. It states that each quantum or photon absorbed by a substance can activate only one molecule. Okay, they are saying one photon is responsible for activating one molecule. Understood? Stark Einstein's law. You can read this. So, this was the introduction which Sir has given in his first lecture about organic photochemistry. You should know among these possible transition, which transition can occur in your organic compound. For that, you should know functionality of your organic compound. Okay, Let's say, let me ask you one question, Prashant. Easy question. Let's say you are given aldehyde, okay, and your nucleophile. Can you tell me among these transition which transition is possible in this case? You can read this slide and then can tell me. Take your time and try. This is your pi bond or sigma bond, this C double bond. Pi na? Have you left the class? Okay. So this is your nothing but your, since this is nitrile is having lone pair, so this is N and this is your pi. But it requires it vacant orbital. So obviously pi star will be vacant. So this is your N to pi star transition. Okay. So this is all for today's class. Thank you for joining my class.